In this session, we're going to look at equations quadratic in form, also called equations of quadratic type. In order to see what's going on here, I want us to recall how we would solve something like x squared minus 2x minus 3 is equal to 0. We would do so by factoring, of course. We would factor this into a product of binomials, x minus 3 times x plus 1, and then set each of those factors equal to 0. We're going to be solving equations that don't look exactly like this, but have this form. That form being, I have an expression showing up twice, in this case x, and the first time it shows up, the exponent is exactly double that of when the second time it shows up. So like we have x squared minus 2x, if you like, to the first power, and then a number. And that's the quadratic form that we're alluding to here. So I'm going to throw something down here that's not really too much different. If we had something like star squared minus 2 star minus 3 equals 0, then you would recognize that star is taking the place of x, and when we factor this into our product of binomials, instead of putting x's as the first term in each set of parentheses, we would put stars in the first term of each set of parentheses. And so that would factor into star minus 3 times star plus 1. And then we would take those expressions, or those factors, and set them equal to 0 and solve accordingly. And what we're, again, doing is looking at a pattern. Well, let's look at our first example, which is solve u squared plus 2u the quantity squared minus 2 times the quantity of u squared plus 2u minus 3 is equal to 0. What I'm noticing is there's an expression that's appearing. The first time it appears, it's got an exponent of 2. The second time, I don't see an exponent, so it's understood to be 1. In other words, this is quadratic in form. The first exponent is exactly double the second exponent. That being the case, what we could think of this as is that u squared plus 2u is playing the role of star. And so when I factor this, I notice the coefficients are the same. 1 for the first term, negative 2 for the second term, negative 3 for the third term. So when I factor this, in place of star, I'm going to put u squared plus 2u. Now let's see what that's going to look like. So I've got square brackets here because we have a parenthetic quantity that I'm going to be putting inside. I'm using kind of a yellow color to indicate where the stars were, star minus 3, star plus 1. And so numerically speaking, the numbers are a negative 3 and a plus 1 inside these brackets. The quantity that's quadratic, the part that makes it quadratic in form, is a u squared plus 2u. And so that's taken the place of the star in the previous equation, which was ultimately taking the place of x in the first equation. Now what I have is two factors that are multiplied together to give me 0. And so I'm going to set each of these equal to 0 in turn. I notice the parentheses actually turned out not to be necessary. And we have u squared plus 2u minus 3 is equal to 0. And then u squared plus 2u plus 1 is equal to 0. Each of these expressions factors. The first one gives us u plus 3 times u minus 1 is equal to 0. The second, u plus 1, the quantity squared, is equal to 0. And so solving these factors equal 0 give us u is equal to negative 3, or 1, or negative 1. Next, we're going to solve a minus 3 over 4, the quantity squared, minus 2 times a minus 3 over 4, minus 3 is equal to 0. You may notice some similarities between this one and the last one. Number 1, our coefficients are the same. 1, negative 2, negative 3. Number 2, we have an expression that is being repeated with that pattern of 2 is the first exponent, 1 is the second exponent. So we are going to solve this by factoring as before, and the kind of yellowy gold color is going to go at the front of the binomials that are going to be the factors. And I'll throw in a -3 and a +1. And so ultimately we have a minus 3 over 4 minus 3 times a minus 3 over 4 plus 1 is equal to 0. As before, we're going to set each of these factors equal to 0 and then solve the resulting equations. So for a minus 3 over 4 minus 3 equals 0, I'm going to add 3 to both sides and get a minus 3 over 4 is equal to 3, and then multiply both sides by 4. A minus 3 is equal to 12, and finally add 3 to both sides. A is equal to 15. The other equation, a minus 3 over 4 plus 1 is equal to 0. We're going to subtract 1 from both sides to get a minus 3 over 4 equals -1. Clear the fraction. A minus 3 is equal to -4. And add 3 to both sides. We get a is equal to -1. I'm going to wrap this up by saying a is 15, comma, -1, which is a fine way to indicate the two solutions to this problem. Of course, you should take the time to check your answer, but we're going to move on. Next, we're going to solve x minus 4 times the square root of x plus 3 is equal to 0. We might be thinking a couple of things. One, there's a radical in this, so I can isolate it and square both sides. So number 2, why is this in this session? Well, we're looking at that form, and what I see is an expression that's showing up twice, that x, but the second time it shows up, the exponent is half of what it is the first time. What do you mean? I'm glad you asked. The square root of x could be written as x to the 1/2. So we have x minus 4x to the 1/2 plus 3 is equal to 0. Since the exponent on the first instance of x is 1, what we have is a situation where an expression shows up a couple of times, and the first time the exponent is exactly double the second time. In other words, this is quadratic in form, with, in this case, x to the 1/2 playing the role of star that we had before. So when I factor this as a pair of binomial factors, I'm going to put the, if you like, the square root of x or x to the 1/2, it wouldn't really matter which one you use, as the first term of each binomial, and then I'm looking at the coefficients. The first coefficient is 1, so I'm not really going to worry about that. The second one is -4. The third one is -3. And so this boils down to simply factoring the square root of x minus 3 times the square root of x minus 1. Setting each of these factors equal to 0 gives us the square root of x minus 3 is equal to 0, or the square root of x minus 1 is equal to 0. And so the square root of x is equal to 3. Now I'm going to square both sides to get that x is equal to 9. And for the other one, the square root of x is equal to 1, which means that our solutions are 9 or 1. We should check both of these solutions for a couple of reasons. One, we want to make sure our work was correct. And number 2, we got to make sure we're not going to get anything imaginary going on. Namely, we can't have a negative solution because we have an x inside of a square root, and that just doesn't fly in this situation. On to the next. X to the 4th minus x squared minus 6 is equal to 0. I see the x showing up in a couple of terms, and I see the exponent in the first term, 4, doubled the exponent in the second term, 2. So, why don't you go ahead and pause the video and solve this. Alright, so I'm going to factor this. We're going to have x squared minus 3 times x squared plus 2 is equal to 0. So x squared minus 3 is equal to 0, or x squared plus 2 is equal to 0. So x squared is equal to 3, and that would give us that x is equal to plus or minus the square root of 3. You were going to forget the plus minus, weren't you? And then the other one is x squared is equal to negative 2. So x is equal to plus or minus I times the square root of 2. At this point, you may be thinking, why are we allowed to have I here when we were all concerned about a negative last time? Last time we were concerned about putting a negative inside of a square root. You see, we had a square root in the original equation. Not so this time. We have no square root in this original equation, so the I is acceptable as an answer. Next, why don't you pause the video and solve x to the 2/3 minus 2x to the 1/3 minus 3 is equal to 0. What I note is that I have the same base, the same expression x showing up in a couple of terms, and 2/3 as the first exponent is exactly double 1/3, which is the second exponent. So I'm going to factor this into binomial pairs, or binomial factors, and I'm going to put x to the 1/3 in the first term of each binomial. You may notice we keep using the guy in the middle. And that's pretty much the norm when we are solving equations quadratic in form. Once you've recognized the pattern, you're going to kind of zero in on that middle term. In any case, we have x to the 1/3 minus 3 times x to the 1/3 plus 1 is equal to 0. So, setting these factors equal to 0, x to the 1/3 minus 3 is equal to 0, or x to the 1/3 plus 1 is equal to 0. The first equation is going to give me x to the 1/3 is equal to 3. Now, it may be tempting to say that x is the cube root of 3, but remember we want to isolate x, which means we need the exponent to be 1. So I need to actually cube both sides. You see that x to the 1/3 represents a cube root. So the cube root of x is equal to 3. That's going to give me that x is equal to 27. Not such an issue with the other one. You could have incorrect thinking and still get the right answer. X to the 1/3 is equal to negative 1 would mean that x is equal to negative 1. But be careful with that x to the 1/3 is equal to 3. Next, we see something that's a little bit different and a little bit similar. Solve 1 over x plus 2, the quantity squared, plus 6 over x plus 2 is equal to 7. Hold up, man. We don't have a 0. Well, we can make that happen. But what's up with the expression? I have 1 over x plus 2 squared for the first term. I have 6 over x plus 2 for the second term. I know that that's not the same. However, this can be rewritten in such a way that we do see a common expression. That common expression is going to be 1 over x plus 2. And again, the first term is squared. But I can rewrite the second term as 6 times 1 over x plus 2. Right? I essentially am using a property of fractions. If I subtract 7 from both sides, then I have that that is equal to 0. So what I have is something that's quadratic in form. 1 over x plus 2 is showing up in the first and second term. And in the first term, it's squared. The second term, it's to the first power, and so the exponent in the first term is exactly double that in the second term. This will factor as usual. In fact, why don't you go ahead and pause this and finish it off. Okay, so my binomials are going to be 1 over x plus 2 minus 1 times 1 over x plus 2 plus 7. Setting each of those factors equal to 0, I have 1 over x plus 2 is equal to 1, skipping a step there, so that 1 is equal to x plus 2 by clearing fractions, and x is equal to negative 1. For the second factor, I will end up with 1 over x plus 2 is equal to negative 7. So 1 is equal to negative 7x minus 14. So negative 7x is equal to 15. And ultimately my answers are x equals negative 1 or negative 15 over 7. Finally, we have solve p to the 6th minus 28p cubed plus 27 is equal to 0. Okay, noting this is quadratic in form and zeroing in on the p cubed, that is the expression in the middle term, I'm going to factor this into a pair of binomials. We're going to have p cubed minus 27 times p cubed minus 1 is equal to 0. So we may be tempted to say p cubed is equal to 27 or p cubed is equal to 1, but don't do that. P cubed minus 27 equals 0. That's actually a difference of cubes, and that factors. Likewise, the p cubed minus 1 equals 0. The p cubed minus 1 is a difference of cubes. So remembering our difference of cubes factoring formula, if you will, we have for p cubed minus 27 equals 0, p minus 3 times p squared plus 3p plus 9 is equal to 0. This is going to give me that p is equal to 3, which I would have gotten anyway, but what I would have been missing out on is the p squared plus 3p plus 9. For that, we're actually going to need the quadratic formula. And when we hit this with the quadratic formula, we have p is equal to negative 3 plus or minus the square root of 9 minus 36 all over 2. In that discriminant, we've got 9 minus 36, which is going to simplify to negative 27, and so we're going to have imaginary solutions. That's typical when we have a difference of cubes. It would also be typical if we had a sum of cubes. Continuing on, p is equal to negative 3 plus or minus 3i times the square root of 3. That's what that discriminant is going to turn out to be, all over 2. I remember I'm supposed to write down complex solutions in a plus bi form. So I'm going to have p is equal to 3, comma, negative 3 halves plus or minus 3 square root of 3 over 2 times I. That's a plus bi form. Now why don't you take that p cubed minus 1 equals 0 and do what we just did, see if you can remember how to factor it, and come up with those last solutions. So when I start with p cubed minus 1 equals 0, I have p minus 1 times p squared plus p plus 1 equals 0. The first factor is going to give me p equals 1. The second factor is going to give me p is equal to negative 1 plus or minus the square root of 1 minus 4 all over 2. As before, that 1 minus 4 is going to give me a complex solution. So we end up with p is equal to negative 1/2 plus or minus the square root of 3 over 2 times I. Now let me wrap up all of these answers in a nice tidy form. We had already p equals 3 and negative 3/2 plus or minus 3 square root of 3 over 2 times I. To that we're going to throw in 1 and then negative 1/2 plus or minus the square root of 3 over 2 times I. This gives us, let's count them, 1, 2, 3, 4, 5, 6 solutions because of the plus or minuses. It may be worthwhile to note that the original equation had a biggest exponent of 6, and that's something that we're going to explore more when we get into polynomial theory. In any case, we have here our solution, and that's all she wrote.